Okay. So my name's Levi, Goals 2021 participant, and I'm going to be talking today about AF C-star algebras, which are kind of really important class of C-star algebras, and I'll touch on a little bit why, how these factor in, why I like them, what's nice about them, etc., etc. So we're going to start off. Um, Oh, there we go. Talking about irreducible representations. And the reason why we're going to go into this is because basically, I guess I should, to not bury the lead, stands for approximately finite dimensional. And so we're going to kind of just start off about what finite dimensional C-star algebras look like. How do we characterize those, and then kind of get into these ones that sort of this sort of next step up that are these approximately finite dimensional ones. And I'll try to give a little bit of time to these and not rush too quickly so you can take notes. But so we call a representation irreducible if there are no proper invariant subspaces. So what this means is that, and if you look in the goals notes, you'll see there's sort of a couple equivalent definitions, but a representation is irreducible if the only subspaces that satisfy that when you take the image of the representation and act on the subspace, that leaves the subspace fixed. The only closed subspaces are the trivial one and the entire thing. So if such a subspace exists, we would call that an invariant subspace. But if no proper invariant subspaces exist, then this representation is called irreducible. And this name sort of should suggest that, we don't really call representations reducible, but if a representation does have a proper invariant subspace, then we should, in theory, be able to reduce it or break it down into representations that are irreducible. And basically, what this little exercise here is saying is that if you do have a closed invariant subspace, ideal, I guess it's proper for making the representation not irreducible, then you can decompose the Hilbert space into a direct summand that is this invariant subspace and its orthogonal complement. And then, in theory, you can, keep sort of repeating this process if you have proper invariant subspaces to kind of break down a representation that's not into irreducible into one that's a direct sum of irreducible representations. And so, yeah, in general, sort of, we like working with irreducible representations. They're kind of sort of the building blocks of representation, sort of the most fundamental ones in a sense. So this sort of I introduced this to sort of talk about finite dimensional C-star algebras and sort of prove the characterization of them. So we say a C-star algebra is finite dimensional if it's finite dimensional as a vector space. Um, so, the kind of ones that jump off the top of our head are the complex numbers, matrices over the complex numbers. Those are going to be finite dimensional C-star algebras. And so, maybe the next question we can ask is, can we classify these finite dimensional C-star algebras? Are there other ones that exist that, we're not thinking about? And so it turns out we have a pretty nice characterization of the finite dimensional C-star algebras. So all finite dimensional, any finite, all the finite dimensional C-star algebras are finite direct sums of matrix algebras. So a finite dimensional C-star algebra has to be isomorphic to a direct sum of these m sub n sub i's for finite direct summands and for finite dimensional C-star algebras. And so this sort of, maybe makes intuitive sense that, all the finite dimensional C-star algebras are just building blocks, finite direct sums of these matrix algebras. And so I'll just kind of sketch the proof a little bit. And this is where the sort of irreducible representations are going to come into play. So if you, using the GNS construction, if we have a finite dimensional C-star algebra, we can view it as a finite dimensional or as a subspace of B of H for finite dimensional H. That's the exercise is 7.21 in the goals notes to kind of see that we can represent this on this finite dimensional Hilbert space. Now, if we have a sub C star, we have operators acting on a finite dimensional Hilbert space, they are necessarily compact. And sort of, I guess, an exercise. I forget it, forget if it's in the notes or not, but every irreducible representation of the compact operators is unitary equivalent to the identity representation. And so we can view this representation as being sort of the identity representation on each of these direct summands. So we can decompose this identity representation into a direct sum of these irreducible representations on these finite dimensional spaces. Um, and then because all of our finite dimensional Hilbert spaces are just these are just these direct sums of these complex number spaces of different dimensions, then the image of those operators has to be a matrix algebra on acting on those things. And so then, using this sort of this picture, we can see that any each of these direct summands, A is acting as a matrix algebra, and so we piece these direct summands together to see that it's a fun for all that if the algebra itself has to be a direct sum of these matrix algebras, and so basically, this is sort of telling us, it's a nice sort of succinct way to say, hey, these are all of the finite dimensional C-star algebras, and if you have a C-star algebra that's finite dimensional, you can find a way to sort of decompose it into these matrix algebras, the direct sums of these matrix algebras, and if it's not finite dimensional, it's not going to look like this. Um, so yeah, maybe these are kind of the first most basic building block examples of C-star algebras, and that's great. And I mean, I guess in some sense there are a lot of these, but we're oftentimes interested in things that are infinite dimensional. And so, thinking about, well, if we're trying to find new examples of C-star algebras, and we can start off with these finite dimensional things, how do we make new ones out of them? And the way we're going to do this is by forming what's called an inductive limit. And this is a really sort of, you'll see this kind of, if you study C-star algebras, we really like to do these inductive limit processes to form new C-star algebras if we have some things that we like and we want to sort of expand this class. So, one way to do that is to create inductive limits out of the C-star algebras we have and then study them.
AKA just union closures in disguise.
Sorry?
Closures of unions,
Yes.
hiding as limits, as I like to think of them. But yeah.
Yes, yeah, yeah, yeah. And yeah, I agree. That I also, maybe if we're a little more analytically inclined, that's sort of a way we want to think about these things and how I often will think about them as well. So, I'm going to talk a little bit about what are inductive limits. And so this is going to be sort of partially based off of the goals prereq notes. And I have a couple other references at the end, but also I like Rortem's K-theory book, chapters 6 and 7. If you don't need to necessarily know K-theory yet to understand sort of what's going on with these inductive systems and these AF-algebras, but that's also another good source where some of this comes from. So I want to talk about just a little bit generally, working in a more general category about what these things are. And one of the reasons that I want to do this is because when we get to K-theory, we're going to be talking about inductive limits of abelian groups. And so once you're kind of familiar with this sort of construction in a more general setting, then you can see that this is just working in a different category, the same sort of construction, and it turns out K-theory behaves very well with respect to these things. And for me personally, I think K-theory is a lot of the value of C-star algebras. I know that's something where we're not getting to, but it's hard for me to not think about AF algebras without thinking about K-theory. So to start off, a directed system, this is going to be consists of a sequence of objects and a sequence of maps between those objects. And the maps have to satisfy two properties. A maps between consecutive objects in this sequence. So the map from uh, AI to AI itself has to be the identity. And basically, the second is saying that these maps compose to each other. So, like, there's a map from any object to any object that's further down the line than it. And the idea is, if you go sort of halfway and then if you go from the halfway point to the end point, then it needs to be the same as just doing jumping, sort of going from the starting point to the end point. So these maps have to compose to be compatible in that way. And I'm just going to, you can think about inductive limits over directed sets that are not the natural numbers. But for our purposes, I think working with the natural numbers is what we need, and it sort of kind of simplifies things. And then if you want to get more sort of fancy with things, then you can use you can use directed sets that are not the natural numbers. So we're thinking about a direct system, sequence of objects, and then sort of maps from every object to each of the objects farther down the line. And we need to be able to compose. If we compose these maps, then they sort of match each other. And we'll get into some examples of these as well. This is a little abstract for the moment. So we want to think about, like, the goal is with this directed system, we want to define what's called an inductive limit. So we want to define a new object that kind of captures all the information of the directed system, and just really kind of packages it all together. And it should be a new object that still exists within our category. So towards this end, we say that an object B with a family of maps, so phi n, so from each object in the directed system into our new object, we say this is compatible with the directed system if for each I less than or equal to j, phi j of phi ij equals phi I. So, oh man, maybe I should draw a triangle here. Let's see how this one goes. So if you have, let's see, we have AI and we have AJ and we have this map phi of IJ. And then we have maps now both from AI to B and AJ to B. And this diagram needs to commute. So if we have an object with maps that satisfy this diagram commutes, then we call this a compatible object. And so we're going to find the inductive limit of a directed system to be a compatible object that is quote unquote universal. Um, so maybe I'll move to the next slide here. Oh, it's still in the annotation mode. Oh, just kidding. It's not on the next slide. Oh, and it does not want to show the whole thing. Oh boy. That's not amazing. Let's see. Nope. Okay. Geez. For some reason, the slide looked better, but I must have missed this. So, um, basically, if you have a compatible system, a compatible object to a directed system that is universal, in that, oh geez, in that basically this sort of any other directed system surjects onto this. The incompatible system projects onto this system, and the maps compose in the right order. So let's see. This should say, let's see if I can do this. So that we basically need for each, we need a sort of a diagram as follows. We need A to B, and we'll call this map row. Oh, that's not how rows go. Wow, why can I not do this? Okay. Okay, and then for any, we'll have A n here. And so then we should have a map, AN going this way. This is Vn, and then AN going this way. Let's see. This should be, oh no, sorry, this is Vn cis ion. That for at each level, we should have a diagram that commutes as follows. So depending on how familiar you are with sort of universal objects, this may be something that's sort of familiar. But the sort of idea here is that this is, I guess, the largest of these sorts of objects that are compatible. And it turns out that if you define it like this way, then such an object will be unique up to isomorphism, and this is what we'll call the inductive limit of this system. Um, so this sort of abstract characterization, I think, is a little, it's hard to just like I don't think it's intuitive to sit down and think about what this looks like. So we'll get into a little bit more detail and work on some examples to kind of figure out how are we really thinking about these things in practice. And like to be fully honest, it's I'm not sitting down with this definition every time I think about an inductive limit. That's not the picture I have in my head. So hopefully we can get through some examples and kind of get a little picture in your head to sort of take away moving forward. Okay.
So yeah,
So, yeah.
unique morphism row going from A to B and then one from B to A, such that when you compose them, you get, depending on which order, either the identity on A or the identity on B, and it gives us like this universal inductive limit object.
Yes. Yeah, yeah. So like whichever one, let's see, you have to yeah, any other object or no, your object should surject onto any other object and have compatible maps. So whichever whichever order the composition has to be identity or
Yeah.
surjective. Yeah. Sorry about the slide. I'll fix that before I post that. Okay. Any other questions? Okay. Why is this? Oh. Okay, inductive limits of C-star algebras. Um, yeah, so basically, inductive limits don't exist in every category, but they do exist in the category of C-star algebras. And so if we have a inductive directed system of C-star algebras, then we can always find a new C-star algebra with maps to make it the inductive limit. And it turns out that this is also, this new thing is the completion of the algebraic inductive limit if you're thinking about these things as just being algebras without a norm. But I'll write this down a little more concretely. So yeah, so as mentioned, C-star algebras do have inductive limits. There's a proof of this in Murphy. There's a proof of this that's slightly different in Rordam. And yeah, so kind of getting a little bit towards how we're thinking about how I like to think about these things, as was previously mentioned in the comment, is that this sort of proposition kind of gives us a little bit of a direction for how to think about this, is that if you have an object that is the closure of the union of a increasing sequence of subalgebras, where we can think about the maps in this union being inclusions, then this algebra is the inductive limit. So when we're thinking about this, it's like we're thinking about we can think about the this sort of this system, and we can think about this universal property, and we can also sort of kind of compactify this information a little bit into thinking about this object being sort of the closure of this increasing sequence of subalgebras in this particular case where we have inclusions, and then this will sort of generalize a little bit when we're not necessarily working with inclusions. But let's just kind of walk through a few details of the proof for how this, why this works. So, just kind of a check to see that if you have A with all of these inclusion maps from the subalgebras into A, that we have this is a compatible system. That's sort of a fairly straightforward check. So, the next thing we need to do is to see that this is universal among such systems. So, suppose that we do have another compatible system. And we can think about an element in A. We can write this as the limit of a we can write this as the limit of things in the as a sequence of objects that are in each of the elements that are in each of the subalgebras in order. And because each of these maps are inclusions, basically, you can think about this map YOTA MN, which is the inclusion of A N into AM. Uh, any object, this inclusion is not doing anything, right? Or I mean, for an object that exists in both AN and AM, it's sending it to itself. So you can think about this object is equal to, if you're thinking about it sitting down further down the line, it is equal to its image further down the line. Um, so now, let's see. So if we have a right, so if we have an n that satisfies that an and am, those are being two different. We're thinking about this as being a limit, right? So the sequence is that sequence has to be Cauchy. So if we're thinking about if you go far enough down the line where where any elements that are farther on from that point are within epsilon, this is just satisfying the definition of Cauchy. And then you apply the map psi. Well, because of this Yoda condition, because of this fact that was mentioned before, that Yoda just is the inclusion that sends each element to itself farther down the line, and then we can psi is a homomorphism; it's a linear map, so we can so we can sort of pull these things together in the psi, and then it's also a contraction because it's a star homomorphism. Then we can show that basically under this image psi that these elements under the map of psi are also Cauchy, and therefore that means the limit of the images of these things under an under each psi n is also Cauchy, and so we can define this map rho from A to B by taking A to basically passing these psi n's through the limit. So rho of A is equal to the limit of the psi n's of an when A was the limit over the a n's. So maybe this is a little bit, I get that reading proofs on screens is a little bit tough to follow. So this is something maybe to sit with and check for yourself if any of the details are a little bit fuzzy. But basically, this is just sort of it's showing us that if we do have algebras where the maps are inclusions, that the inductive limit is just going to be the closure of the unions of each of these subalgebras. And it's sort of, kind of the proof that you would sort of think about trying to write down and trying to do, and just sort of passing this other map through the limit. So yeah, I think when I think about inductive limits, this is, this sort of compatible ideas of like in general, if you have the inductive limit of a directed system, then the limit has to be equal to the closure of the union of the image of the subalgebras under these maps phi that are defining the inductive limit. And so, if we're kind of a little bit maybe more analytically inclined, then we want to think about, these sort of unions of subalgebras and then closing this up in the norm versus thinking about this system and these sort of compatible maps. You kind of have these two different ways to characterize these things. And this is sort of, leading us right into the definition of an AF algebra. So we've kind of talked about what do our finite dimensional algebras look like. We've sort of talked about what do inductive limits look like. We have these two different pictures, one where we're thinking about just kind of the system, and one where we're thinking about, the union of these things. Now, I will say the one thing we need to be careful about when we're trying to think about these sort of unions and these closures is that the maps in the inductive system do matter. So it's sort of easy to think about, oh, like what are the subalgebras? What are the subalgebras, and really focus on that. And that obviously can shed a lot of light on what the algebra looks like. But it is also important that the maps do make a difference, and so we need to kind of keep those in mind as well. So getting to AF algebras. So we say a C-star algebra is AF, or approximately finite dimensional, if it is isomorphic to the inductive limit of finite dimensional C-star algebras. So these are precisely the C-star algebras which arise as inductive limits of these direct sums of matrix algebras. And sort of kind of tying these things together, these sort of two different ideas is that C-star algebras AF, if there exists an increasing sequence of finite dimensional C-star algebras such that are basic that are dense in the algebra itself, and if that is true, then A is equal to the closure of these things. So if you're looking at a C-star algebra and you want to know whether or not it's AF, one thing you could do is try to find a sequence of finite dimensional C-star algebras that are dense inside of it. Okay. So these are um, the kind of algebras that we're looking at today. So let's look at an example of an AF algebra. And this is probably my favorite AF algebra because I like working with dynamical systems and cross products and like dynamical systems acting on the Cantor set. And so this nice example is a commutative C-star algebra. It's the continuous functions on the Cantor set. So we call a space a Cantor set if it is totally disconnected, compact, metrizable, and has no isolated points. And we'll say a Cantor set or we'll say the Cantor set because there is a unique space up to homeomorphism that satisfies these properties. And so we can think about there's a whole bunch of different models for this, but the one which maybe you're most familiar with is this middle third Cantor set. So this sort of Cantor set, and I'll get into a picture once I talk about Bratteli diagrams, but this Cantor set that you've probably seen at some point where you remove the middle third at the first level. Now you have the first third and the last third. And then if each of those chunks you remove the middle third and you remove the middle third and you move the middle third going down and down and down. Now, this sort of process is, very much fits into this framework of what we're looking at for an inductive system of finite dimensional algebras. So at each level, for our can for the continuous functions on the Cantor set, each finite dimensional algebra is isomorphic to C to the 2 to the n, which is precisely that is the continuous functions, or that is the complex numbers multiples of the indicator functions on each of the partitions. So if we think about looking at the sort of the first level of partition, we have 0 to 1/3 and 2/3 to 1. And you're thinking about the continuous functions on these on these two different pieces or sorry, rather the complex number of multiples on these two pieces. And so we're thinking about constant functions that are locally constant. And so each of these things is we can think about that. That's sort of the first level. That's C to the two-dimensional complex numbers. That's the first level, and then the next there'll be four, and the next are eight, and the sort of the inclusions are given by the partition where you think about it. So the continuous functions are going to be are the functions that are locally constant are going to be dense in the continuous functions, and so you think about the function that's 1 on 0 to 1/3, well, and maybe 0 on the other one, then it embeds into the next level as 1 on the first two of the four, and 0 on the other two. And so each level, those are finite dimensional C-star algebras. And so the closure of these things is the continuous functions on the Cantor set. And so we can write the continuous functions on the Cantor set as this inductive limit of these sort of these functions that are constant on each level of partition. And this is precisely what we call our AF filtration. These are our this is the way we're seeing this as an AF algebra. And so in particular, it's nice because it's commutative. It's each level, you're looking at direct sums of the complex numbers and not more complicated matrix algebras. And you have this sort of nice, sort of structure that's given by the partition. And so, you notice that there are a bunch of different partitions you could get to get this Cantor set. But in the inductive limit, they're actually all going to be the same algebra. Okay. So I think this picture, you have this in mind of this Cantor set, we can envision these middle thirds, and it kind of leads us nicely into what are called Bratteli diagrams. And so this is another really nice way to sort of describe and visualize AF algebras. So a Bratteli diagram is a directed graph. It consists of a set of vertices. So similar to how our AF algebras, we had our sub-algebras that were sort of ordered via the natural numbers. We have the same thing. We have vertices where at each level we have a certain amount of vertices, and then we have edges from one level to the next. So you can think about with this Cantor set, instead of having these sort of intervals, these one-third intervals, we could think about replacing those with we're just going to say there's a vertex each one of those, and we're going to say, there's an edge between each interval and the intervals that it splits into. And so, yeah, we have a set of vertices. We're going to call this the disjoint union of our VNs from 0 to n ranging from 0 to infinity. We have edges ranging, our disjoint union of our ENs ranging from n equals 1 to infinity. And then we have our source and range maps, which are going to take us from the edge set, are just going to take an edge, and the source map is going to associate it the initial vertex, and the range map is gonna associate it to it the end vertex. So if you've talked about graphs, I think there might be a talk on graph algebras, but if you sort of, this stuff will come up again when you're looking at graph algebras, or if you look at graphs, etc. And yeah, as mentioned, right, the idea is that each edge connects a vertex at one level to the edge to a vertex at the next level, and the source being where it starts, the range being where it ends. And so the way, the sort of last bullet point is how these Bratteli diagrams relate to these AF algebras. So if you do have an inductive limit, and viewing the nth level of the inductive limit of, sorry, if you do have an AF algebra, inductive limit of a sequence of finite dimensional algebras, and the nth finite dimensional algebra is sort of this direct sum of these matrices, then the Bratteli diagram we can think about is that, at the nth level, there's a vertex for each one of these direct summands, and the connecting maps are going to determine the way that the edges, where the edges go. So, if you have a matrix algebra and, depending on how it's embedded into the next algebra, that we're going to have, one edge for each time that the matrix is embedded in the next one, or each time that the matrix algebra is embedded at the next level. And I realized sort of sitting here without, the kind of first example of the Cantor set, we'll go to the Bratteli diagram. I mean, some of these edges might be a little bit confusing without kind of a picture in your head, but the idea is that, you're breaking this up into each levels, and, when I'm thinking about these things, I'm really, when I want to think about this is like each level is kind of being embedded into the next one, and how many times is this thing being embedded? Like that is going to determine how many edges there are from one vertex to the next. Or, maybe this is embedded into one of the matrix algebras and not both of them, or something like that. And that's sort of where these edges are going. And so, yeah, it turns out that, this is a really nice way to describe an AF algebra is via these Bratteli diagrams. So, just looking at the AF algebra for the Cantor set, this Bratteli diagram, we have the complex numbers, and we basically have a copy of the complex numbers at each sort of level of this partition, or at each element of the partition, really. And this is sort of indicating that, like, if you have a constant function on one level of partition, it breaks up into, constant functions at the next level. And so, this will sort of going on, and this tree will sort of branch out. And you can see this is kind of this visual of like you keep this process going on and on and on. It's sort of mirroring what's happening with the Cantor set as you break things apart. And at each level of partition, you're just sticking a copy of the complex numbers because those are your locally constant functions. Your locally constant functions are going to be dense in the continuous functions on the Cantor set. So not all and by the way, so I should say like the reason why this C-star algebra is commutative, right? It's like the complex numbers. It's the only matrix algebra that is commutative, and so there's a complex number at each stage, and that's how you end up with a commutative C-star algebra. But most of the time, we're going to end up with matrices of different levels. Yeah, so just kind of looking at this, right? The vertices these are the character. We can think about this, topologically, like these are the characteristic functions on the clopin partitions, and the edges between them is just refinement of the partition. So, you're taking a partition, you're splitting it up in two for the next level, and that's how kind of what's encoded in this Bratteli diagram. Okay, so another example that is that we I like, I guess, that comes up a lot. It's sort of related to some of the dynamical systems I study as well. Is called the Carr algebra. So CAR stands for like classic anti-commutation relations. It has a lot of applications to physics, which are not my research, but a lot of people are interested in the Carr algebra for that reason. And so this algebra is isomorphic to the closure of the union of these matrix algebras, these matrix algebras whose dimensions ranges over the powers of two. And so we can see this kind of in this system, this the way that these inclusions are, you have C into the 2 by 2 matrices, the 2 by 2 matrices into the 4 by 4 matrices, the 4 by 4 into the 8 by 8 matrices. And the map in between each of these things, you take a matrix and you put it in twice. Um you put it in as you put it in as both the top corner and the bottom corner. And so this is how you're getting an inductive limit based on these things. So you can think about this matrix is sort of doubling in multiplicity as it goes up each time. And so the binary, okay, the sorry, this is it's a slight mistake here. There should be two arrows here. So the Bratteli diagram here is at each level you have these 2 by 2 matrices, and each time you're getting embedded with multiplicity two into the next matrix algebra. So you're thinking about, you have the complex numbers, they embed twice into M2 on the diagonal, M2 embeds in M4, M4 embeds to M8, et cetera, et cetera, et cetera. And generally speaking, like when you're thinking about just looking at an inductive system and what are your like the reason why like the size of these matrix algebras has to like if you just looked at the maps you could figure out how big each next matrix algebra had to be because you need to make sure that you want these maps to be injective. And so wherever you start off with, depending on you may be looking at I'm thinking about this because I've like looked at, you look at examples and you're looking at a matrix algebra, and maybe it doesn't tell you, you're looking at an inductive system and you need to figure out which matrix algebras are living at each level. And, this, you kind of need to enlarge the size of the matrix algebras in order for this map to be injective. So if you want to put two copies in, you put them in along the diagonal, and you need to double the size each time in order to fit each of the matrix algebras in. And so, one thing, I don't know where you are in the von Neumann algebras lecture, but if you look at this algebra and these maps, this should, if you've seen the hyperfinite to one factor, if not, keep that in mind. Like, um, this is sort of the system, this is the diagram that you would see for that, where you have this embeddings in these two to the n dimensional matrix algebras. As n increases, everything sort of being put in along the diagonal similarly. And yeah, so there's sort of a big contrast between the von Neumann and the C-star algebras in this realm, where you have C-star algebras, you have all of these really, you have a lot of different AF-algebras, you can change the dimension of these matrices, you can change these maps, and you get a whole bunch of different C-star algebras. Whereas in the von Neumann algebra case, all of these any von Neumann algebra associated with these systems is going to end up being like isomorphic to the hyperfinite to one factor. And so there's sort of a big dichotomy here between what's happening in the C-star case and what's happening in the von Neumann algebra case. Now, these Carr algebras are a nice example of what are called a particularly nice class of C-star of AF algebras that are called I just not want to are called UHF algebras. So these are uniformly hyperfinite algebras. So these are AF algebras that are sequences, are the inductive limits of a sequence of full matrix algebras with unital embedding. So basically, what this means, as we saw before with the Carr algebra, is that at each level, the matrix, we don't just have a direct summand of a bunch of direct sum of a bunch of different matrix algebras. We have just matrix algebras at each level. So this is you have M2 of C, you have M4 of C, you have M8 of C, and these are a very nice class of C star algebra of AF algebras. They're sort of nicely understood because of these matrix algebra. Because you're just working with one matrix algebra at each level, and in fact we have sort of a very nice classification of these UHF algebras via via supernatural numbers. So, the Carr algebra, that was sort of the first example of a UHF algebra that we have. But we have this really nice characterization where two UHF algebras are isomorphic if and only if the supernatural numbers associated to the inductive systems are the same. So just kind of slowing that down for a second, like when you have a UHF algebra, you have matrix algebra of a certain dimension, but in matrix algebra of a certain dimension. And so if you look at the numbers on these dimensions and you sort of put that a supernatural number is basically it's a formal product of infinite natural numbers, and sort of basically you can think about this as having an infinite prime factorization, and if the infinite prime factorizations of these things are the same, then the supernatural numbers are the same. But it's sort of a neat kind of way that we can characterize these algebras that they're isomorphic if and only if we can classify them based on these sort of supernatural numbers, which is sort of a neat thing. So it's sort of you can see that there's infinitely many of these UHF algebras right away, and actually sort of uncountably many because we have sequences that we can work with, and so that's sort of cool that even just looking at these building blocks of starting from these building blocks of these finite dimensional just matrix algebras that we can build uncountably many C-star algebras using these UHF algebras. And so yeah, this is a very nice class of example subclass even within those AF algebras that are very nice to work with. The Carr algebra being sort of unique or not unique, sort of one of the nice ones to start with to get a feel for what these things look like. So as I kind of mentioned, a really sort of valuable tool in the kind of creation of new C-star algebras is this inductive limit process. So there's a whole bunch of inductive limit type classes of algebra. So AI, AT, AH, ASH, these sort of, AF being approximate in all these cases, just thinking about, well, what happens if, we took inductive limits of finite dimensional algebras and that gave us a really nice class of C-star algebras to work with. What happens if we think about, so inductive limits of circle algebras or interval algebras or, continuous functions on X for X sufficiently nice spaces. And, this is a really kind of, when you're thinking about, we have a result for C-star algebras, it's a very natural question to ask, well, what happens if you pass the inductive limits? Does this result hold? And, one of the things that's really sort of working in our favor with this is that K-theory behaves very nicely with respect to inductive limits. So basically the K-theory of the inductive limit of a system is the inductive limit of the K-theory in a group. I know you haven't looked at K-theory yet, but I think it's sort of one of the really nice sort of things about these inductive limits is that if we can kind of write them down, that we really know what happens with K-theory, and you can learn about it from K-theory. And it's just sort of highlighted in the classification of AF algebras by their ordered dimension groups with order unit. So basically, this very nice little invariant for these AF algebras was kind of a big sort of motivating point for Elliot as we move forward in the classification program. And yeah, in general, classification is, I mean, I guess, maybe it's not, I was going to say it's obvious, but, by the end of this, sort of goals course, I think it'll sort of hopefully be instilled on you that the classification program has been a huge accomplishment, huge undertaking, huge motivating force in the study of C-star algebras over the past, generation or two. And it's sort of, guided a lot of the work that we want to do. And so these sort of, inductive limit processes are really really useful in creating new classes of algebras. And it's really sort of interesting to see how C-star algebras sort of behave under inductive limits and things like that. And so, you know, if you're always, if you're working at examples and trying to understand things, AF algebras are really nice to work with. You start from finite dimension, you go from there, and it can be fun to just kind of, write down Bratteli diagrams and play around with those things. And yeah, they come up in a lot of they have a lot of really nice properties, and so it's very nice to kind of look at what's happening with AF-algebras and try to extend that to other classes and things like that. And when you have this sort of finite dimensional grounding, this sort of dense union of finite dimensional algebras, you can really do a lot with that. And so, kind of you're interested in sort of learning more about these things. Yeah, the references I had, I looked at, the goals notes are obviously very nice. There's some exercises in there. That are good to work on. There's a, so Murphy, shoot, I forgot to put what chapter what is, but there's some information on Murphy on some of these inductive limits and AF algebras. And then, I also, maybe putting a little bit of my own personal bias, but I like Rortem's chapter 6 and 7 on these things. It's all sort of in the context of K theory, but the stuff for AF algebras is you can learn all that stuff without necessarily knowing what K theory is yet. But hopefully in a few weeks you'll know what K theory is, and that'll sort of kind of further motivate these topics a little bit, and just kind of thinking about the link between K theory and AF algebras inductive limits is something that really sort of grounds kind of my understanding of this topic, and I think it's sort of a helpful sort of next step once you've kind of gotten a little bit of feel for these things, worked on thinking about these as Bratteli diagrams and inductive limits and these sort of the closure of union sort of picture, and trying to get a feel for these things. And yeah, so I think AF-algebra is a really nice class of algebras. There's not like there's a lot of research that we've done on them. They're very, very well studied, very well understood in general, but they're really good motivating examples, and they also kind of provide us good jumping off points for hey, how do we want to generalize, what happens in the AF case, and how do we generalize this to more complicated inductive limits, or more complicated processing, things like that. Um, so I think I'm going to end there, and I will stop recording.